quantum theory of the atom. Before we go into depth about the quantum theory of an atom, let's talk about the nature of light. A wave is a continuously repeating change and oscillation in matter or in a physical field. Light is a wave. Light consists of oscillations in electric and magnetic fields that can travel through space. Frequencies or wavelengths of electromagnetic radiation is called the electromagnetic spectrum. Visible light, X-rays, and radio waves are all forms of electromagnetic radiation. The characteristics of a wave. A wave has a wavelength, which is the distance between any two identical parts of a wave, and a wave also has frequency, which is the number of wavelengths that pass a fixed point in one unit of time.
The best part about the quantum theory of an atom is the part that we can actually see. That is called quantum effects. Quantum effects is quite simple. It is the light or energy that is coming off an atom at any time that we can see it. The light that we can see is caused by photons that are given off when energy is applied to an electron. When energy is applied to an electron, it kicks out to a different level and releases a photon, like when a car releases its exhaust. Quantum effects change greatly from element to element, since they all have different masses and densities. Because of the different masses and densities, the atom will vibrate and move quite differently. The smaller the mass, the more likely you will see quantum effects. The two most popular quantum effects are fluorescence and fireworks. They seem very different, but they're actually quite similar. Fireworks quantum effects is caused by heat energy, which is applied to the electron, which kicks out the photon, which releases the different colored light depending on what element it is. Like I said before, different masses, different elements, all different colors. Fluorescence works quite similarly, except instead of heat energy applied, is light energy. When the light hits the electron, it kicks out a photon, and that's how our highlighters get so bright.
If light moves in waves, then other matter may move the same way as well. And here we see the de Broglie relation, lambda equals Planck's constant over mass times speed. This equation illustrates the wavelength of nearly any moving particle, which is incredibly small. Unfortunately, de Broglie's relation doesn't necessarily hold true for all things, such as electrons, for it only applies to particles under normal circumstances. Electrons are under magnetic forces from the nucleus and even themselves, and therefore travel about randomly. Because electrons are so small, only 9.1 times 10 to the negative 31st kilograms, there really is no definite way to know its path or even its position around a nucleus. This can be explained by the Heisenberg uncertainty principle, which states that as more is known about the position of an electron, the less is known about its momentum, meaning we can never be certain to where it is exactly. However, there are areas of probability where an electron may be, or where it may be going, called atomic orbitals.
There are four quantum numbers which describe an electron. First is the principal quantum number, denoted by n, which describes the energy level of the electron. For example, if light or heat or some kind of energy were to strike the electrons, they would jump to a higher energy level, moving further away from the nucleus and becoming more chaotic, expanding the orbital. The principal quantum number may be anything from 1 to 7, which is determined by counting down the periods, starting with 1. The next number, the azimuthal quantum number, is used to identify the different orbital shapes and is denoted as L. Each energy level, principal quantum numbers, have different shapes that the orbitals can have. When n is 1, it will have only one possible shape, a sphere. When n is 2, the orbitals will have up to 3 different shapes. 3 will have 5 shapes, and when n is 4, will have 7 shapes. These areas of concentration are called lobes, and as n increases but L does not, the orbitals will grow, for the electrons will travel further away from the nucleus. The way to determine just which is which is to first look at this table. All of the elements in the S area will have a spherical orbital. Those in D will have this shape. Those in P will have this shape. And those in F will look like this. When labeling, first write the principal quantum number, and then the azimuthal quantum number. Third number A magnetic quantum number simply determines where the electrons will be in the orbital. It is denoted as m sub L and is different for each energy level. A final number, a spin quantum number, is just the way the electrons may rotate, and is denoted as m sub S. The only values are negative 1/2 and positive 1/2.